Hey, what is going on, guys, and welcome to our third signal processing tutorial. Today we're going to cover the differential op-amp. Now this will be our last ideal op-amp video, so enjoy it while you can. I've chosen this op-amp because it looks quite difficult in comparison to the ones we've been doing so far. But once you get into it, you'll realize that it's no different, and we're using the same rules and same laws, and we're applying them in the same ways and following the same methods, and it'll all be good. What are we given here? Well, in this video, I've done things a little bit differently, and I've given you the gain equation. So if you feel inspired at any time, feel free to pause the video, try and work through it on your own, and if you can get the right answer, that's great. If not, don't worry, we'll go through it right now. Okay, so let's get started. We'll use a Kcl equation at our node Vx. That gives us our current I1 entering, which can be given by V1, minus the voltage at this node here, which is Vx, divided by the resistor R1. And then that's equal to current I2, which is given by Vx minus Vout divided by R2. Okay, so in our final answer, we don't have Vx in our gain equation. So we're going to solve this equation for Vx, then we're going to use another Kcl at our node Vy and set that equal to Vx as well, and then we'll relate them to one another to find our gain. So let's do that. First, we'll multiply through by R1, R2, because you know how much I hate denominators. That will give us V1, the R1s cancel, R2, take Vx, R2, and then all of that's equal to Vx R1, take Vo R1. So we'll get all of our Vx terms onto one side by adding Vx R2 to both sides and adding Vo R1 to both sides. That will give us V1 R2 plus Vo R1 is equal to Vx, and then we'll just collect our like terms here, R1 plus R2. Awesome, so now we can divide through by R1 plus R2, which will give us V1 R2 plus Vo R1. All of that divided by R1 plus R2 is equal to Vx. Okay, so nothing's too difficult yet. Let's use another Kcl equation at our second node, Vy. Now, I hope that you noticed that as this is an ideal op-amp, the voltage at this point, V+, is equal to the voltage at this point, V-. Therefore, Vx and Vy are essentially the same thing. So let's call this Vy Vx. So let's move on with our Kcl equations. We have I3 entering, which can be given by V2 minus the voltage at this node here, Vx, divided by the resistance, R1, and then that's equal to the current leaving I4, which can be given by Vx minus ground, which is simply 0, divided by R2. Okay, so I think you might know what we're going to do here. We're going to multiply through by R1, R2, and that will give us V2 R2 minus Vx, the R1s cancel, R2, is equal to Vx R1. Now, as we did previously, we'll move all of our Vx terms to the right hand side. So we can do that by adding Vx R2 to both sides. That will give us V2 R2 is equal to Vx, we'll bring it out the front again, R1 plus R2. Then we can divide through by R1 plus R2 to get Vx on its own, which will give us Vx is equal to V2 R2 divided by R1 plus R2. Okay, so we now have two equations in terms of Vx. We can set those equal to another and it will remove Vx from our equations. Let's do that. I'm just going to cheat real quickly and get a copy of this. We can notice that the R1 plus R2 is common to both sides, therefore it cancels, or in other words, we can multiply through by R1 plus R2. That will give us V1 R2 plus Vo R1 is equal to V2 R2. And remember, we're trying to find Vo divided by V2 minus V1. So we can subtract V1 R2 to the right hand side of our equation, which will give us Vo R1 is equal to V2 R2 minus V1 R2. Then we can collect our like terms as R2 is common to both terms. R2 V2 minus V1. Then we can divide through both sides of our equation by V2 minus V1, which will give us VO R1 divided by V2 minus V1 is equal to R2, and we're getting real close now. We can divide through by R1, which will give us VO divided by V2 minus V1 is equal to R2 divided by R1. And we got our final answer. Okay, well, I know that one was a bit longer than usual, but thanks for sticking with us. I hope you can see now that any of the ideal op-amp questions that we do will always have a similar method to this. There might be multiple Kcl equations which you have to take, but in the end, they'll all be using the same rules and the same laws and very similar methods, so you should be able to do most circuits which come your way. In the next video, we're going to tackle a non-ideal op-amp. Now we're going to start with an easy one for that. I hope you enjoyed this video. If you had any problems at all, feel free to leave a comment down below and I'll hopefully get back to you, and I'll see you guys in the next one. Thanks.